Okay, now we're going to sit back and have some dry math a little bit. This dry math is going to really summarize what we've learned so far and viewing things, maybe preparing us to go to multi-layers. That's the goal. So here I'm just basically establishing the notation. So every time you come across things, you have to say what the vector dimension is, what the input was. So I'm just documenting that for you. So I have an input in this case. We're saying the input is m dimension. We have a single output, exactly what we just talked about. And we have a weight, which is just a row. This row is a row vector of dimension 1 cross m, 1 by m, right? Same description. And I'm leaving this k because if I have many outputs, I'm selecting one of those outputs, the kth output in this case. And I think I mentioned to you before, we cannot, have a universal notation. Every time we have to say what notation you're using, establish that, and move on. Every paper you read is going to have its own notation. So you have to develop some kind of resistance to being derailed by this stuff. So here's my notation. And in this case, I don't worry about the bias, so I'm basically lumping the bias as part of the input. I can take the first component, the last component to be equal 1, I'm done. And I have this linear relation. A vector of input, m dimension, and an output is a scalar in this case, and therefore this kth is the kth row, because I'm anticipating I'm going to graduate this into a matrix, right? So I'm selecting one of the outputs, I'm applying this. Here's the error signal, scalar signal. And my work that I just described for you right now gives me the gradient descent, translates to this particular update equation. So what I have from the eta is just basically an outer product between a scalar E and transpose of this input signal. And that really is the gradient at every instant, every in sample that comes in, at sample n. Exactly what we talked about. So if you move to the next level, say, okay, let me have, instead of one output, we have R outputs. What is this picture here? The picture is very similar. We have the R output. We have a matrix instead of a row parameters. We have a matrix of parameters, W. And we have X. So if the output is R and the input is, in this case, M dimension, then the matrix is going to be of dimension what? R by M, right? Again, now we have the error signal, the same as we did before, except now it's a vector error signal of dimension the same as the output. You're given this D, which is the label, which is the desired value. And gradient descent, or the online form of gradient descent, because we don't see the operator here. I'm just having, I have it in my head, but I'm not explicitly showing it there. It's going to be the present matrix weight, how to move to a better choice of weight at the next time. We add eta, which is a parameter I have to scale. Typically, you want it to be as small as possible, so you don't have any instabilities. Okay? And then it's the same form. And I have in parentheses here is the analog continuous form of this equation. This equation, instead of the weight at time n and the weight at time n plus 1, we have the derivative is equal to the gradient. Any questions?
You said eta. Is eta the same thing as step size?
Well, eta we refer to as the learning rate. It relates to the step size. It relates to. But if I take this equation, the differential equation that I've shown you here in parentheses, and I apply an approximation of this derivative, let's begin with the Euler approximation. How many people know that? Which is really W of n plus 1 minus W of n over the step size. I can derive the discrete equation. So when you derive it, basically, it turns out that this eta relates to the step size, unless you have other factors. So it's scaled of the step size. So if you notice in this equation, I have a gamma here, right? So this eta becomes gamma times the step size, if you want to be precise. If your choice of approximation of the derivative is Euler approximation. But all of us know Euler approximation is the first order approximation. There's other approximation, Runge-Kutta approximations, fourth order, and all other detail. So from the differential equation, which is really the true gradient system they're dealing with, you can get a lot of different approximations with various degrees. Okay? We're opting here for the simplest representation by Euler approximation. Very good. So now the only parameter I need to come up with, this parameter eta, people came up with a nice fancy language for it, which is called hyperparameter, to differentiate it from the parameter, the weights and the bias. Just a fancy word that says hyperparameters. Hyperparameters, these are parameters on the outset, before you run and execute the algorithm, you have to make a decision on. So on the outset, you have to supply your algorithm with those you have to make a decision, or at times you have to make some mechanism that maybe adopts or adapts these hyperparameters. But these are often things that you make a decision on independent of the gradient descent, often labeled as hyperparameters, which is it's like meta parameters or additional parameters that you have to worry about. Okay. So in this case, we only have, in the discrete form, we only have eta as a hyperparameter. Okay. And this one could be shown, could be derived from a Euler approximation of a continuous time true gradient descent. Okay. I'm sorry, so here. So one thing that we have, when we focus on this equation as a discrete equation, matrix equation, we can also have other approximations, not Euler approximation, but more advanced approximation that will lead us to a result where we have another parameter here. So note, note here, we don't have any parameter multiplied by the present value. But here you have a parameter which is sometimes the literature referred to, in the systems literature referred to, or numerical techniques literature referred to as forgetting factor, or stability factor, or forgetting factor. Okay, all these different terminology, and its purpose is to make sure that I have the weight. I'm going to scale it a little bit, but a factor less than 1, close to 1, but less than 1, before I add the gradient to predict the other one. So there's a forgetting factor. So I don't want to have it all equal to 1. And this is an intuitive approach, but also due to stability issues, that's another important approach. Because when you look at this linear matrix equation from a stability issues, it has a matrix which is the identity, which eigenvalues equal 1, and 1 is actually the boundary of stability and instability of linear discrete systems. So you want to be far away, lower than 1 in terms of, so you have insert this alpha for a discrete system to basically add stability, okay? Which is close to 1 but less than 1 and more far away from 0. Another choice in practice sometimes, these are numerical techniques that people use when they crank out or execute these equations. This eta, you may want to relate it to the alpha that you choose. So if alpha is close to 1, sometimes you make this eta equal to 1 minus alpha. In that case, the choice of the parameters is called convex choice because it has the convex property. And often they find it to be performing better in the approach. Any questions? Any questions? And what I have in parentheses here, the justification for how you insert this alpha from the true gradient descent, which necessarily comes from continuous systems. If you have the gradient, you insert basically a stabilizing element here, which is minus some factor epsilon W, which is for stability. It's like you have the eigenvalues in the left half plane. Anybody who's taken like transfer functions or linear systems know that this often adds stability for this differential equation, because it is a differential equation here, discrete equations here. So this alpha here is stabilizing factor because you have a discrete dynamic equation. Okay? Any questions? So now we're going to move one level towards feed-forward neural networks. The first wrinkle that we're going to have, we're going to say, okay, we dealt with linear filter, linear systems. What if we have the equations here. This is the input, this is the weight, okay? And instead of directly equal to the output, we have an intermediate variable. In this case, I'm calling it v of nu, another vector. This side here, a linear equation, like the previous one. But I'm going to take this guy, and I'm going to hit it with a nonlinearity to get to my output for this filter. So I'm going to have a nonlinear filter, single stage, single layer, but having nonlinearity. What does this do in this case? I can walk through the steps. We have the error signal. When I do the derivation of the gradient, and which I've done before. We've done before in the derivations. We took the derivative. I talked last time about the chain rule. In the chain rule, we have derivative of nonlinearity. That nonlinearity we call here phi. Okay? And other times we're going to call it f, sometimes psi, so please do not be disturbed by that. Okay? Every time we call this nonlinearity, we have to tell you what it is, and different times we select different representation. Okay? So this choice here is phi. It turns out the changes that it impacts, the only thing is you have derivative of if this nonlinearity is a vector. So this is a vector. Okay, I'm telling you all the vectors of R dimension and the weights, and the difference between this one and the previous one, you have a derivative of nonlinearity. And mathematically speaking, if you have a vector of nonlinearity, you take the derivative. Mathematically speaking, if you want to keep the linear algebra, that's going to give you a diagonal matrix with derivatives of the component-wise. Okay? So view this one here as a diagonal matrix with the diagonal elements are the derivative of the components of this nonlinearity. So it's a matrix. So now I have this matrix, which is from before, multiplied by another matrix, and the 8. So the only thing is that, unfortunately, I put the E here. So the E as before, the only thing is that we have derivative of nonlinearity, which is in this case, is a matrix, diagonal matrix. By the way, this diagonal matrix, you can also replace it by a vector of the diagonal elements, which is derivatives, and perform a point-wise multiplication, okay, with this E. So you have this E. So we have an E, which is a vector. Time is a diagonal matrix. What does that mean? That means the first element in the diagonal multiplies the first component of E and so on, right? Which is the same as point-wise multiplication if this guy, derivative, is a vector and this E a vector. Why am I saying all that? This particular multiplication procedure is referred to as point-wise multiplication, and also known in mathematics as Hadamard representation, which is represented by a dot with a circle surrounding it. A Hadamard representation. Why am I saying that? I'm saying it because in coding, often people, instead of having this diagonal matrix, a lot of zeros, which means you have to store everything, they use this Hadamard multiplication for efficiency, and you represent the derivative as a column vector of the diagonal elements, and you do point-wise multiplication. Another reason for it is that in Python, for example, the star, which represents multiplication between two column vectors or two matrices, is a point-wise multiplication by definition. Okay? You have to look at something called np dot np dot, np point, and then dot. That's the function that's used for for multiplication of normal matrix by vector multiplication. Okay? So you're going to see in all the coding thing, when you look at it, you're going to see this one implement these two things in red. Instead of a matrix, diagonal matrix, and a vector, this is going to be represented by a vector of these diagonal elements, pointwise multiplied, which is Hadamard multiplication by this vector. And that's how it's often implemented in coding. Okay? So in this thing here, the only thing we have the derivative. Okay? And it turns out, in this case, this nonlinearity at the end doesn't really change any of the scenario. If this nonlinearity is so-called one-to-one, which is often we use, like the sigmoidal function, the hyperbolic function, or the rectified linear, or any other basically one-to-one nonlinearities, is going to preserve the same properties, meaning that you still have a single optimal point, and if the corresponding Hessian matrix is positive definite, that point is going to be a global minimum. Adding nonlinearity at the end and having it does not change the picture in this particular case, if the nonlinearity is invertible, okay, which is one-to-one. Any questions? Yes?
When you said nonlinearity being invertible, you mean, what do you mean?
It has an inverse.
Oh, has it?
Yeah, invertible means has an inverse. So when I look at the sigmoidal function, the inverse is also exists. Yeah, you have an inverse. The hyperbolic tangent, you can flip it an inverse. Okay. The rectified linear doesn't really have an inverse, but it approximates a function that is actually invertible. Okay, any other questions? Any comments? Okay. So I'm going to see if I can move to the next level, which is what happens when we have these same layers with nonlinearities, and then the output of this one becomes driving a similar module. And we have multi-layers. That's how we get the multi-layers. So we have many of those layers, which is really linear operation, nonlinearity, and then linear operation, nonlinearity, and so on. You could decide how many of those things. I have notes here, which are, by the way, I have a folder which contains all the last year's notes, which I recommend you access those before class and familiar. I'll be updating maybe some of those things as we go along, as I see it's necessary. But if you want to prepare and you want to look at what notes, these are viewed as the skeleton notes that you could bring in and you can write on them and expand on them or ask questions, okay? So for example, I have this note 3.1, which basically has looks at the pointwise derivations of multi-layer neural networks pointwise, and looks at the update law and okay, so maybe I'll quickly walk through this one here quickly. Okay, so if I have so I have an input for simplicity, modularity of the equations. We could view an input and we can label it as some x. I think what I need from this one here, I need to basically bring your attention to something like this diagram, which I have it in a PowerPoint, but it's not available at this point. So this is an abstract graph, okay? And let's see if we can walk through this one together, okay? So you have an incoming data stream, okay? That data could be a scalar, could be a vector, could be a matrix, but we're going to assume that this data somehow is a general vector. And in this case, we have this S is the signal. Okay. So let me see if I can make it better, center it. Because the description here is going to, detail those things, but I need the diagram to be able to discuss it here. So this is an end-stage feed-forward neural network with a back propagation architecture. So let's step through the process. So first look at the black diagram, okay? So this black diagram, I have S sub k, which is the sample. Let's say I'm using k as the index, and it's a vector. This incoming vector is going to multiply this matrix W1. And I have the bias B1 has an input, which is in this case +1. You add them together, you're going to have W power 1. Okay, and that gives you a variable here called S sup 1. So this is another vector, X sup 1. And if you notice, I change the variables here. And the reason I'm using X1 here for this notation, that it's going to represent the state for the first layer. Ignore the red stuff. Just look at the feed forward coming from the input moving towards the output. X1 gonna pass through the circle, which is nonlinearity, the first nonlinearity. We're gonna call it F1, F sup 1, whatever your choice nonlinearities, and you're gonna spit out an output. And in this case, I'm selecting the notation that's currently used in many places, A instead of Y. A stands for action, or actuation, or activity, or A sup 1. So this is like the first stage. And then you repeat the process. A1 is going to apply W2, and you have plus B2, and then move on, and you have in this case n stages. And you see regular staging, cascaded, one feeds the other one to get the final output. And at the very end, that's where you call your output. You say, here's my output. Every one of those circles represents either a linear function, which means you don't have any nonlinearities. For example, often the last stage, sometimes people refer to have linear output. And you have nonlinearities. So that's the cascade of neural. So there's nothing difficult about it. Just a cascade of feeding neural network. And the depth concept comes when you go deeper. And the winning projects right now, and some of these big competition, ImageNet, what have you, they have deep networks that go over, certainly 150, 200 of these multi-stages. Now, with me, imagine that every one of those X's that we have here is going to be a representation, because this representation X is obtained from the previous output, okay, by a transformation, matrix transformation. So what do matrices do? Matrices rotate signals or scale them. These are the two things that a matrix does. And then what does the bias do? The bias is just going to shift it. So if you have coordinate system, you add a bias, you're going to shift the position, right? And a matrix is going to be rotated and scaled. These are the two things that can do. No, nothing more, okay? So if you want to have a nice description of this one, you're going to call the first signal, just for make it, call it A sup 0. Then I can mathematically, compactly write this iterative equations, okay? Nested equations, okay? And at the very end of this thing, that's the output of interest. So the X is here, transformation. So transformation, you hit it with nonlinearity, and you transform. So there's a nonlinear transformation, which really, what it's doing is really unwinding any complexity on the data itself. So if you have a data that is non-linearly separable, meaning that the data is so much together, the classes are so intertwined, okay? What these transformations are doing are basically transforming this data. Hopefully, if you are succeeding in this process, at the end, this data will be nicely organized. Things that are similar will become in one nice cluster or class. And at the end, you succeed in classifying this data or approximating this data or detecting this data, or even predicting if a new variable comes from this data. So you with me on that? So that's really the intuition behind it. And this description here, by explicitly having x, which is going to become the state, just tells you like a different coordinates. So every x here represents a different coordinate system. Okay? And you basically, the transformation from beginning to end is not linear. It's a cascade of nonlinearities. And because of the presence of the parameter, we can succeed in approximating any bad nonlinearities. So it becomes a universal mapping, parameterized universal mapping that, driven by the data, can succeed in approximating any complexity. Okay? So I hope I can find, okay, so I can, I guess I'm going to stick here, maybe it's safer, because I may not find what I'm looking for. I don't want to spend the time. So basically, with this picture, if I move here, what do? At the end of the thing, you call this is my final output. I have this input. So the output is going to be a function of the input, nonlinear function through this mapping. It's not it could be any parameterized mapping. And what do you do for supervised learning? You have a label at the end. You have the error signal. You, for example, have a cost function, which is represented by the L2 norm in this case, a choice. There's so many more sophisticated choice than this one here. And you have the cost function. And this cost function implicitly is a function of all the parameters of this network. So if I have n stages, this cost function will be viewed as a function of all these matrices. Matrix 1 sup W sup 1, all the way to W sup n. Each one of these is a matrix, and you have the parameters, okay? And with your patience here, this is the way I'm going to write. This whole graph, I can write it in this compact form. So I'm taking the first input, I'm labeling it a to the super 0, whatever, and I have this one equation, and I have an index I, and I have this compact form represent any size of n stages. So if you get tired of drawing the diagram because you reach the end of the page, this equation, you could draw it, compact everything in one hand. This is the model. And this is a nested, cascaded model with parameters, okay? And we explicitly have the weights as a matrix and the biases as vectors, okay? And you can have any nonlinearities. And I'm labeling this output here. I explicitly show you here that you could, whatever it is, this is your net, which is this cascaded net. And I'm sorry, I'm going to quickly jump to the so-called backpropagation, which is with the sensitivity equations. The stuff that we've done carries over in basically generating an intermediate network. We create from the description a network, which is called the backpropagation network or sensitivity network. So in the single layer, we only have the error. But the multi-layers is going to lead to not the error, but some network of errors. The error at the end layer, which is the nth layer in this case, is going to drive a network, okay, all the way to the beginning layers. And that's something we created from deriving the gradient descent, okay? And I have in the notes that we have here a lot of forms, basically, of of showing how this network is extracted from the derivation of the gradient descent. This network, when you do the gradient descent and you use the chain rule, you discover that I don't have to bookkeep all these things here. I'm going to define something intermediate variable, which is the lambda here, which is the delta function or the co-state. And when I collect those things, I'm going to have a network. Right now, we're just jumping ahead and describing the network, and we'll show the derivations later on. So this network is going to take the error at the very end, which is here, which is we already have the error, right? And you take the error, and this error is going to pass through the derivative of nonlinearity, like you've seen in the equations, which is this derivative is going to be a matrix, diagonal matrix. So diagonal matrix, or you can do the pointwise multiplication to obtain an intermediate vector. This intermediate vector, we define it to be some delta or lambda. This is a vector, which is a transformation of the error from the final stage. Same error here. And the same index I have for the network, I'm going to apply it an index to this intermediate network that we are using for modularity, for simplicity. And then this lambda, which is a transformation of the error at the final stage, is going to multiply the same matrix of that layer, the ith layer, transpose. So because of dimensionality, this has to multiply the transpose to get a transformed error at the earlier layer. So this starts from n and moves all the way to layer 2. So when you begin, this is e to the n. It's going to give you lambda to the n. Lambda to the n is going to give you e to the n minus 1. So you're going backward in deriving this letter. This network is a extracted network from the derivation of the gradient descent to make things intuitive and simple. You don't have to do it. You can just crank out the gradient descent, and you don't take any advantage of it, and just compute that mathematical expression. This one just makes it so it's modular in a network structure, so you can actually compute things locally when you need it. And then finally, if you have this original network, which you already derived, and you have this shadow network that you create, which is extracted from the derivation of the gradient descent, which we'll revisit to derive it just for completion. Then the update law, the gradient descent, which is really the update, the change for each one of the weights for any one of those layers, is going to be simplified to the same form as in the single layer, which is an outer product between two things. One, which is related to a transformed version of the error, which is, we call it lambda. And the other one here is the output of the previous layer, which is the input to the present layer. This is the structure maintained to be similar to the single layer that we've seen. So before we had only have one error because it's a single layer. Now this error is going to be driving a network and has transformed version of it at each one of those layers. These transformed versions are going to be called lambdas in this case. And it's going to be the same transformed error with the input to that layer. The indexing of the layers is I. I have n layers. The I here indexes the layer now. And it's going to be the same outer product as it has a single layer. That's the beauty of it. It's just so nicely structured that's ready for realizations. Okay? So this is the change of the weight that you need to do every time you supply an input or sample. This is a change. And if you have multi-samples, mini batch, you have to take an average of these guys. This is the change that gives you that gradient. This change is equal to the gradient direction, which you need to use to add to the present weight to have a better weight that accommodated this new information of the data. Same thing for the bias. The only difference between this one, the weight, and the bias is that the bias doesn't have any input because the bias input is always +1. So you drop it. So that's the beauty of the equation. So this equation, so if I go back to the diagram, and I want to explain this whole idea, and you can invest time with looking at the mathematicals and the equation in the notes. But if I go to this picture, I can explain this whole equation of this diagram. So I can write the form of the equations from feed forward. So you have an input signal, passes through, you go to the end, you compare the output with the desired value. That's the error. You bring the error here, e to the n. That e to the n is going to drive this shadow network. This shadow network is related to the forward network. And if you notice that these boxes here are going to be related to the derivative of the nonlinearity, and the weight's the same weight, but it's transposed, and you have the lambda, which is the transformation of this error. And you have all these lambdas. And every weight for every stage is going to use this local lambda times the input to this layer, out of product, to update to check the change. So the change is going to be lambda 2 times A1 to change, and so on. So you can have all the update from this diagram. If you get this diagram, you can do the math. If you have the math, you can do the diagram. And often, after you do it so many times, the math, you don't have to do the math every time. You just go to the diagram and get it, and you get the gradient descent. I'm going to stop at this point because I'm going to begin next time with this one here. And I want you to read the notes, okay? And the update folder that I have, only if I need to update something. But you're going to rely on the existing notes as they stand. Thank you for your patience.